Okay, so today we will talk about things called directed systems and direct limits. So this will be like, I'll do some exercises from the textbook, but the exercises will build the theory of directed systems, direct limits, things like that. So this is question 14 in the textbook. So I'm going to write a lot, but there are some things we have to check. So a partially ordered set, let's say I, is said to be a directed set if for each pair of elements in the set I with there is a k in I such that I is in k is less than or equal to k and j is less than or equal to k. So the application of this directed system is if A is a ring and let's say I is a directed set, and you will see soon, Guni, why these directed sets are important.
Why is it important?
Because, well, actually, I will say something and then you'll say, why are those important? And then maybe you can help. So we have a directed set I, and then we have a family of A modules, and they're indexed by I. So for each, let's say, I and j in the directed set with I less than or equal to j, let mu ij be a map from mi to mj, such that first of all, mu ii is the identity map. I'll write it this way. This is just the identity map on mu I for all I and I, and the second is if the second condition is if I is less than or equal to j, which is less than or equal to k, then we have a commutative diagram. So we have mi goes to mj by this mu ij, then there will be this j is smaller than k, so there's a map that way. But then that means I is less than k, but then also this diagram has to commute. So if that's the case, modules mi and the homomorphisms mj, I'll just say homs mj, let's say, form a direct system. And we have to keep the information all together, so we make a collection and we put it together as bold M over the directed system, let's say I. Do you know any objects that behave like direct systems?
Sheep.
Yes, and why are sheep so important? Okay, so let's construct a new A module M, and this is the direct limit. This is not good notation. How about this? How about I write this like this is m bar. I'll call the direct limit m, but it's the direct limit of m bar. So a sheaf is actually direct limit. It's some example of direct limits of abelian groups. But in abstract algebra, we usually just call abelian groups just modules. So where was I? Yes. So let's see. Oh, I'm sorry. There are direct limits of sheaves, but not all sheaves are direct limits. Sorry, I made a mistake. So C starts off as a direct sum of the mi, and let's just say from now on you see mi and C, but the image I'll just call mi in C. So from now on, forget mi, just consider mi. Let D be the submodule of Ci, it's of C generated by all elements of this whenever x is less than or equal to j. Then finally, let's say M is C mod D. And let's say mu is a map from C to M such that each xi goes to projection. Yes, and then this goes this way, and then let mu I going from mi to m just be just like an xi goes to xi bar. Okay, so the proof that m is a module is very simple. We don't have to check much. So all of these ideas are very clear. It's clearly a module because it is the quotient of two modules, both of which are modules, so you can take quotients. The only issue is we need to check that the action of A on D is stable, meaning A dot D has to live in D. And the way to do that is simple. Let I be less than or equal to J.
So didn't you define D as just the smallest sum module, so that, I mean, as an A module? So isn't it just obvious?
You just have to make sure that the action of D keeps inside D. It stays inside D, or else the action will not be well defined on the direct limit.
I mean, the definition of D was defined as a smallest module.
Yes. So it's the module generated by all of these types of elements, xi minus mu ij of xi. Whenever I is less than or equal to j, I and j are in I. Yes.
So this is already a module.
D is a submodule of C. Yes.
So why should we need to check that D is stable under A action?
Because or else it's not a well-defined group operation on M, or else M equals C mod D will not have
got it. You're
yeah.
checking the well-definedness. Okay.
Well-defined group operation.
Yeah, thanks.
Good question. But so how do we prove this? So just show that A times D lives in D. So to do that, let I and J be in I with I less than or equal to J. So prove that A times xi minus mu sub ij of xi is in D for all A in A, xi in mi. Well, that's clear because A times xi minus mu ij is the same as A times xi minus A times mu ij of xi. And because you have a module homomorphism, it commutes with the action of the ring. This is exactly what I wanted. And so that's good. And so this is a well-defined group operation. So M, the direct limit, is in fact a module. So from now on, we can call M to be something like this. So this is usually the notation. So let's move on to question number 15. So I will warn you, my solution is very technical and I've lost some of the details since I last did it 6 months ago, 7 months ago. So again, you will be familiar with this idea, this mathematical idea. So again, let M be the direct limit of like some collection mi in some directed system I, and then so 15a is show that every element of M can be written in the form of some mi of xi. So it just looks like all.
Did you roll mu II for the homomorphism?
No. So this is this map.
Got it. Yeah, thanks.
Yes.
Thanks.
This is what I mean. Yes. So so I want to prove that if something looks like this, it's just, I'm sorry, ui of y, I, for some I. So how do I do that? Well, so you only need to prove that for finally many places. So let x be in M. That is the quotient space, quotient module. So C, remember, is the direct sum mod D. So actually, X is the same thing as I'll say xi is in mi. I'll say xi is non-zero. So x is just like some tuple of these elements from mi, which are non-zero. Only finally many of them are non-zero. So I only need to prove the answer for xi plus d. right? So if I prove it for xi plus d, and then I just add everything together. So let k be the max of all those I. Sorry, overall the xi. Then for each xi plus d, this is actually equal to mu I k xi plus d. And so if x is actually just the tuple of this, that's the same thing as saying it is the sum of all of these, I'm sorry, mu I k of xi plus d. But then this is all are elements of mk. So I can just say x is equal to mu k of, I'm sorry, xi. Yeah, and so we're done. So every element of the direct limit is just some injection from one single group. Okay, so that's the easier of the two questions. So this next question might also be familiar to you. This is the gluing axiom of a sheaf. Sorry, not the gluing, the axiom for pre-sheaf, I think, not the gluing axiom for a sheaf, for a pre-sheaf. But right, so here it says let xi be in mi such that mu I of xi is xi plus d is 0 in M. So this is extremely technical, but I'll try to recreate it in a way that is a little bit clear. So if this is true, then xi is an element of D, so that means that xi equals some some collection of things like this. So I have made some notes. I said that note that if we have that ij from these indices ij, if any of them are less than I, so like if any of them are less than this I, then we have that aij is 0, and thus we have naturally that mu ij plus 1 of aij is 0. So we only care about indices greater than or equal to I. So I will say let R be an index, or let's say will be the, how would I say, R is the largest, I'll say index, which is non-zero from that above. So I claim that mu I R of xi is 0. So this is what I have to prove. We may assume that we have a totally ordered set of indices, and I'll say I is the smallest, then there's some R1, then there's some R2. I don't know how many R's there are, but the last one is the biggest, and I'll say that's R. So, so this is the setup. If you go back here, I will try to find all the possible cases where you'll have this sort of decomposition. Let's say for one of the indices, I say G3, we have, I'll say A G3 minus mu G1, G3 of X G1 minus mu G2 G3 X G2. Imagine this piece comes out of the decomposition up here. So then I said that then that means for the G1 index, for the index I said G1, we have that XG1 must be 0. And thus we have mu G1, G3 of X3 is 0. And so we don't have to care about this piece. So I made some comments. I'm not going to write everything down. I'll say this is a question of pigeonhole principle. To prove this claim, I said that the way to prove this is if you have n minus G1 slots for this element to go into, then there are total of n minus G1 possibilities for mu I G1, I said. And so if one of the slots has 2 mappings, so like we have 2 mappings for the G3, then one of the slots has no mappings by the pigeonhole principle. And if we pick G1 to be the smallest such mapping, then the G1th coordinate is just XG1, and so XG1 is 0, and so mu G1, G3 of G1 is 0, so we can do this. So from now on, I prove that if we have X is in D, then X equals something like A1 minus mu, I'm sorry, I'll say I1 is, I don't know, J1 of, sorry, mu J1 I1 of, sorry, other way around. plus a I2 minus mu I2 mu j2 of a I2. So it's always going to be pieces like this. There will never be like a piece that comes from somewhere here and it gets inserted here. So it won't be like a4 minus mu of mu 2 4 of a2 minus mu 3 4 of a3. It's always going to be a2 minus mu1 2 of a1 plus, I don't know, a4 minus mu 3 4 of a3, etc., etc. No single row has two mappings in it. Okay, so that's an important step to make things much simpler. So let's say that let's say we have each summand looks like ARI minus mu RJ RI of ARJ. So except for the first entry, which is, let's say, x1, and the last entry is, I'll say, negative mu RIR of, I don't know, some XRI. So it looks like x1 plus, I don't know, like A RJ minus mu RK RJ of ARJ. Sorry, I switched it again. Plus minus some mu RI RX RI. So if we don't have this of this form, then we can do some reduction because some things will always be 0. Then I'm saying that mu IR of xi is mu RI R of mu I RI 1 of xi, and that equals mu RI R of ARI1, which is the same thing as mu RI2R mu RI1 RI2 of ARI1, and then this equals mu RI2R of AR2. So what I'm trying to say is all these elements map and they collapse down. I will finally say there are finally many steps between RI2 and R, and then we keep going until we hit negative mu Rn minus 1 Ra Rn minus 1 equals 0. That's what I wanted. Okay, so it's very technical, but if you start with some small case examples, you can see that there's a lot of reduction before you have to actually prove the real question. So these directed limits have like a way to keep everything in order, both groups and maps, and of course they're very important in things like you said, sheaf theory, things like that. Okay, so
I think I need to see the proof again. I don't follow 100%.
I think I made some statements in my own head, which I did not write down clearly since a couple months ago, but yeah.
Got it.
So like in chapter 2, we talked about the tensor product. So tensor product is a question of a universal object. I will show that direct limit is characterized up to isomorphism by the following property. So let's say let N be an A module, and for each I in the directed system I, let alpha I go from Mi to N. Be an A module homomorphism such that I have that Mi goes to N, and then Mj goes to N by mu j, I'm sorry, alpha j, alpha I, and then alpha ij whenever I is less than or equal to j. And then I and j are an I. And so I'm going to say, then there exists a unique homomorphism alpha going from M to N such that, so you have alpha I going from M to N, and then I have M, and then here I have this mu I is commutative. So I claim that M, the direct limit, is the universal object for this type of property. So how did I prove this? So to start, this is very hand wavy. So I will say that, so this alpha, what is alpha? What is this map alpha on M? So M, remember, like I said before, it's the quotient of a direct sum. So alpha is a modular homomorphism that is completely determined by where it sends each tuple. Let's say something like xi 0 plus d. If you tell me where alpha sends each of these elements, then you tell me what alpha, the map alpha is. But alpha of this element plus d, this is actually alpha of mu I of xi. So this is just mu I of xi. And then, so if you already know what this is supposed to be, here they said this was supposed to be commutative. Sorry, this is supposed to be alpha I of xi. So if you already know all of them, then you know what alpha is supposed to be. And then to prove that, I have to prove that alpha is well defined. Namely that if we have indices I and j, one is less than the other, I need to prove that alpha of xi minus mu ij of xi behaves nicely. So this is alpha of xi minus alpha of mu ij of xi. And then this is going to be alpha of mu I of xi minus alpha of mu j of mu ij of xi. But then by that property, this is just alpha I of xi. And by that property, this is just alpha of alpha j. This is, this is alpha j of mu ij of xi. But that's just the same as alpha I of xi minus alpha I of xi. Because these maps commute to get you just alpha I. And so this is just 0. That's good. Okay, so we haven't proved anything yet. So I'm going to say let M prime be another module with these properties. We need to prove M is isomorphic to M prime by a unique isomorphism that commutes with alpha I. So, I mean, this is just a question of replacing, let's say, something like alpha I n with, let's say, alpha I m prime, or maybe I should have written a different index. I'll say mu I, because that's what we started with. We get a unique map J going from M to M prime, such that I'll say alpha I is J of mu ij. And then if we switch the roles of M and M prime, we get the same thing. We get such that I'll say that Mi is J prime of alpha ij, and we also have that J of J prime and J prime of J must be the identity. It's kind of like the same copy of the proof of the tensor product being unique. Okay, so how much more time do we have?
Up to you.
I think this is not a bad place to stop.
Sure. So the argument you showed so far is first by using the commutative relation to define the map, and
Yes.
it just implies the where defined is, you just show it. And because you use the commutative relation, so even though we choose another map having the same property, so it must be actually isomorphic.
Yes, exactly.
Yeah, got it.
So I didn't write all the details.
Yeah,
but
it doesn't matter.
I think I wrote enough.
Okay, then as you said, then I will stop here.
Okay, thank you.